All right, 12-1, day 1. First couple of slides, we're going to basically revisit some ideas from Chapter 3 based on linear regression, because Chapter 12 starts to revisit that a little bit. Okay, so this data here is kind of interesting. A teacher took the time to kind of revisit the old idea that, if your desk is set up into rows, that's sitting in, the front row is advantageous and is good to do because you'd be more likely to learn more and for your test scores to be better. So some students took this on as a project. I guess it was more the students that really convinced the teacher to do it. But here's what they have for a chapter where they randomly assigned everybody in a class of 30, I think, 30 or 32. Probably says somewhere in there. I think it's 30. And you have for each student the row that they sat in, and then their score for that chapter. For example, if we were to just kind of randomly select, this student right there, we would say they were assigned to row 3, and they scored 88. Okay? So there's basically just the data itself. So here is where we really revisit some stuff from Chapter 3. So the first thing it says to do is to make the scatter plot. In class, we'll go ahead and do that. I'm not going to take the time to do it here. I mean, the one point I highlighted, there's 388. Right? I'm more concerned that you feel like you know how you would do it. I know we've made scatter plots before, but there's 30 points, and I don't want to go and plot all of them right now. It would just take too long. But in class, we'll do it. But I'd rather spend our time over here that we get into R, which tells you the correlation. Okay, now it's a little bit of a surprise here if we just dive into the correlation, because if you were to make the scatter plot first, well, then you could just look at it and have a pretty good sense of what it was going to be. But you can go stat calc 8 and see that it is negative 0.218, which would tell you, obviously, it's negative. If I were describing it, the scatter plot does look somewhat linear, but it looks really weak. A little bit negative, really weak. That would make R squared about 0.0475. Okay? So we think about 4% of the variability that we saw in test scores would be accounted for by our line that compares it to the row the student sat in. Okay? Which isn't much. I mean, maybe to some extent the variability, which was slightly negative, that as you went back from one row to another, that you were more likely to get a lower score, but it's pretty weak, and you're only talking about, maybe a little bit of your score dictated by the row that you sat in. Okay? Under stat calc 8, we could also get the regression line, which would be 85.7 minus 1.12x. Okay? 85 is your y-intercept. Remember, that may kind of extrapolate your data. Here, that would be your predicted score if you sat in row 0. Well, that's wonderful. There is no row 0. We had the options of 1 through 7. And then the slope is negative, so I want to get into that on the very next page. Here's the interpretation for our slope. For each additional row a student sits from the front, the predicted score will decrease by 1.1 points on average. Okay, that association was pretty weak as well. Okay, so it's also not even that steep of a slope. That, you know, as you go back a row, you'd predict the score would go down about a point. We'll get into conditions here in a minute. Randomness would obviously be really important. You wouldn't want to let students choose, right? Because then their ability could really take over, and the more, theoretically, the higher achieving students may want to sit up front, and lower achieving may want to go to the back. And whether that's the case or not, we don't want to worry about it. We would much prefer that every single student was randomly assigned to the row that they got. This we'll get to in class. It's kind of a fun little simulation where I want to make note of it right now because it gives you a good indication of where we're kind of headed. The slope that we got from that class is a sample of 30. Okay, and we have seen for a long time now that measurements from samples vary just due to chance. Okay, so if another class had done the same experiment with 30 students, could they have gotten a different sample slope? And by this point, I think you're probably pretty convinced that the answer is yes, they probably would have. We're going to take a look at that and see, all right, that's kind of one thing to say, yeah, those sample slopes are going to vary, but we're going to want to get into how would they vary? Like, would they follow a normal distribution? Standard normal, like a Z, or perhaps would it follow a T, or is it something brand new? And how much? Like, how much variability would you expect? So that's really what this is going to, we need everybody together to do this in class, but we're just going to build a dot plot and look at all kinds of sample slopes. This I'll just touch on for a little bit because I just want you to know they're there. Okay, so we're used to, when we talk conditions, I hope you would think random and normal. Because when we're dealing with means or proportions, that's where we focus. Chi-squared, random, and large numbers. Okay, we know independence is kind of there, but we don't typically address it. So we have realistically 3, but we consistently address 2 conditions. If you were to do like an interval or a test on a slope, which in the next 2 sections, or the next 2 lessons, we're going to do, you have conditions, okay? If you're doing an interval or a test for a slope, they have 5. There they are, okay? So now you can go one of 2 ways with the rest of this lesson. There's only a few minutes left. I take you through what each condition is, okay? There's no point you would ever be tested on conditions. So if you wanted to stop, you could. You don't need to know them. And you might think, because of that, why, if we're not going to test on them, why would I even take the time to show them to you? Because it's kind of 2 different things for me. I really don't care if you know exactly how to verify all the conditions. Okay, they are pretty messy. But I want you to know that they're there. In the past, I've skipped over these conditions, and I find it kind of leads students to believe that, if we're doing an interval or a test for a slope, they don't have any conditions. And it's like, no. They do. They actually have 5 fairly picky conditions to do it. We just don't test on it. Those are 2 totally different things. So I can deal with the fact that you know that, okay, we're not going to be tested on conditions if we're doing a slope, but they're there, and we have them, okay? I spelled the acronym liner. All right, the first one you've actually kind of seen that you should, that's like an R and a scatterplot kind of thing. You should verify that the association is actually linear. Independence, that's normal, right? That we've seen that before, not like normal distribution, but independence is like always a thing, that each individual piece of data should be independent of the other. Normality, that's a tricky one, refers to the residuals. So that's where it gets a little crazy, that we'd have to go make a histogram of the residuals to kind of see if they're normally distributed. E, so both of this is, I think, worth noting. These are both about the residuals. They should be normal, and they should have equal variance where about half of them are positive and about half of them are negative. And then random is always there, right? Whether random sampling or random assignment. So for the example we had, here's kind of how things would look. The scatterplot shows a weak linear association. Right along with that, the residual plot doesn't show any obvious patterns. Which is also good, right? If you remember back to residual plots, that's what we're looking for, okay? And we would need to address both of those things for the condition. Independence, we're assuming that their scores were all independent. Normally you could go one of two ways here. The histogram, these are of the residuals. The normal probability plot of the residuals, we saw those once upon a time, that what's going on here is it takes a piece of data and compares it to its z-score. So on this axis right here, you have a residual, and then they get the z-scores of the residuals. And there you could really do either or. I think this would be your more common bet, that you would just look at a histogram of the residuals. Okay. We did see once upon a time with a normal probability plot, we had seen that it was more common that you have the kind of the x, like the raw score that was your x variable compared to its z-score. That should look linear. Okay, but this is, we're looking specifically at the residuals, not the x or the y value. Equal variance. We have half positive residuals and half negative. And randomness, that students were randomly assigned to their seat. Okay? There you go. There's 5 of them. They're wicked. Again, my purpose in all this, you know that they're there. And that, you know, if you're doing a test or an interval on a slope, that we'll do in the days ahead. There's conditions. If you want to never, you know, look at them again for the rest of this course, that is completely acceptable, and you can just forget about it. But I've made you aware, and that's all I was after.